So I'm going to talk about work that's in, there's a number of papers, and so I'll be brief about some of the details. But basically, what the project's about is trying to find ring-like solitons in field theories. These are dynamically stable, so they're called Vortons in the cosmological literature, but they're essentially just stable vortex rings. So there is an application which was alluded to this morning in cosmology, and there are also strong analogues to the Gross-Pisovetsky equation. There's a whole way of writing what I'm about to say, which you could do analogous thing in that, but I'm actually going to talk about the Lorentz invariant versions. So the starting point is what we call the U1 cross U1 field theory, but basically it's a Lagrangian for two complex scalar fields, phi and sigma, interacting with a potential which has essentially got second order and fourth order terms. And later on in the talk, if I get to it, I will also talk about the inclusion of gauge fields. And there's an extra parameter there, a coupling G, and then there are these parameters. There's two lambdas, two etas, and a beta. They're the interaction coefficients. And phi will essentially be, when I get to talking about the vortex case, will be an embedded vortex, or it may also be a domain wall in the two-dimensional case. And the sigma will be what we call the condensate field. So sigma is always a complex field, phi will be a complex field or a real field. So the sort of starting point for this discussion in the cosmological literature was a paper by Witten in 1985 on superconducting vortices. And basically what he said was that the field theory that I've just written down essentially has a conserved current in it, a so-called Noether current, which leads to a conserved charge. And that conserved charge is analogous to it's the relativistic equivalent of the integral of sigma squared, which is used in the non-relativistic literature. And he then constructed solutions using the ansatz that I've got here. So there's a phi is the vortex field. So there's a profile function phi of r and a vortex theta, similar to the ones that we've been, very similar to the solutions that have been talked about by a number of people in this meeting. And then sigma has a profile as well, but it also has a z-directed twist, okay, kz, and a time-dependent omega. And so you can work out profile functions for these, the profile functions that solve the equations for a given omega and a k. And so the green one is for sigma, and the red one is for the vortex. So the vortex starts at 0 and goes to some expectation value, and the condensate starts at 0 at infinity and goes to some constant value in the center. Okay, so it's just a vortex, but it's got a twist, essentially, in the z direction. Now, I'm going to define this parameter chi, which is omega squared minus k squared, and basically the fact that there's a twist in this direction means that there's a current along the vortex, and you can characterize this by this thing as being either what we call magnetic, electric, or chiral, and it depends on that's to do with whether the current is null, space-like, or time-like. So the idea of Vorton is to basically take that solution and embed it in a ring-like solution, as I've illustrated here. So now the twist, rather than being in the z direction, is around the azimuthal direction, and there's a vortex in the other direction. So the question that I basically want to sort of study is whether for a given q and n, and q is related to omega, and n is related to k. So n is the number of twists around the axis here, and q is the total charge that's basically on this Vorton. Can you find stable solutions? Now there's actually an analogous paper we wrote some time ago about trying to do this in a Bose-Einstein condensate as well. Now it's actually quite a difficult numerical problem because there are many parameters in the theory. There are 3 in the global theory and 4 in the gauge theory, and in order to create a stable solution, you have to we're going to do all this numerically. You have to fit it in the box. You have to make all your core widths and things like that inside the resolution. So you've got the radius of the Vorton, the width of the vortex and the condensate, and the trapping potential for the condensate. And you've got to make them all sort of nicely aligned in your box so that you can find solutions. So in order to do this, you have to actually start quite close to the right radius, which of course has to be inside your box as well. So actually we found it sort of very convenient to actually go to 2 dimensions just to start with, and replace this complex field with a real field, and make a choice of parameters, and this is the choice that we made. And actually for the z-directed, or the equivalent of the z-directed string, it's actually y-directed because there's only 2 dimensions. There's a y-directed twisted domain wall solution, which goes from -1 to +1, parameterized by this parameter chi, and chi has to lie between -1/4 and 1/4 for this particular choice. And so these are the equivalent of the superconducting vortex solutions. These are superconducting domain wall solutions. There's actually an exact solution for all values of chi, and that has well, here's a picture of what I'm talking about. So here's a kink solution, and there's the condensate. So this has some real power to what we're trying to achieve, because it actually allows a semi-analytic formulation of this problem to know the exact solution. So if I give myself a value of q and n, I actually can predict what the radius of the associated what we call kinky Vorton solutions exist. And so basically we've done a whole load of things. We then found the solutions via gradient flow. We evolved them in the field theory. I'm going to show you some examples of this, but I'm not going to go into all the detail. We evolved the full dynamics and showed that they're all stable. We actually managed to create them from random initial conditions, and we actually even created an equation of state for the wiggles on the string and showed that all the stability properties of this system. So here's some just brief examples of what we did. So for example, for a given q and n, so these lines are what the analytic prediction gave us, and these dots are solutions that we managed to relax during our numerical solutions, and they fitted exactly on the line of where we predicted where they would be, at least for sufficiently large q. So that's one of the things we did. Here is where we just evolved these ring domain wall solutions in radial dynamics, and we started this one off. We knew that its radius should be 50, its stable radius should be 50, but we started off with a radius of 70, and it evolved down and eventually settled down to the stable value of 50. So that was all very good. We also looked at the stability to perturbations in the azimuthal direction given by some coefficient n. So n is the number of wiggles around the loop, and you can actually work out a Lagrangian for the perturbations and do a whole analysis, and we can show that for example for chi here, all these ranges were actually unstable, but there's actually a stable region here. And in fact we could even predict, I don't think you can quite see it here, but there's a numerical evolution from the field theory of the oscillation of a loop which is actually unstable for this. I think it was one with n equals 4, this, and we evolved it forward, and we predicted the exact radius at which it would evolve to in time, so, and it did do that. So, but the most important thing we learned from the original problem that I wanted to study, which is the study of the three-dimensional problem, was actually the choice of the parameters. And we found that the choice of parameters that we were using here was not the most optimal so one of the big sort of issues in this game is to actually find a solution where the radius is small enough to fit in your box. And the ones, we define this parameter gamma, which is some strength of the trapping potential of the condensate on the, which traps the vortex. The vortex potential that traps the condensate. And we found that in the electric regime, which is the best one for finding solutions, that there was a different choice of parameters, which is slightly different to the one that gave an exact solution, which actually made the thing stick on the string better. So we use that in our three-dimensional simulations. So how am I doing for time? No, well, how long have I had? 5 minutes left. Yeah, okay, all right. So back to 3 dimensions. So we use the set of parameters that I said in the earlier slide. We basically solve, we have put in an ansatz now, which is a 3-dimensional ansatz for a vortex here, which I've missed the e to the I, the angular part of the vortex there. But the main point is that the sigma field is rotating by n around the azimuthal direction, and we minimize for these functions phi and sigma here using what's called the cartoon method for a given n. And we were actually able to find static solutions as a function of n. These are the radius. So as n increases, the radius increases. For q, relatively small, we could only find a small range of values, but for q, very large, we were able to find a wide range of so-called Vorton solutions that were stable. We did radial dynamics for these guys as well. So here's one where we predicted the radius, we got the radius right, we put the right radius in, and it just sat there. Here's one where we gave it slightly the wrong radius, and it sort of, as before, oscillated down. And here are the full field dynamics. So the pink stuff here is that's the energy density, and the green is essentially the number of twists of the field this is the real part of sigma as you go around the loop. So this is at t equals 0, and for 300 300 units of time, it stayed there, and then eventually it became unstable. But it became unstable to something that's essentially an n equals 4 mode, which is the square box, which, going back to what I said before, I think that's probably what's, there's this picture here, this one here, so n equals 4, there's some regime which things are unstable to n equals 4, and I think that we were in that regime. So we then tried to do this in the gauge field theories, where we now have a gauge field parameterized by this as an extra parameter, the gauge coupling. And we were able to find some solutions. So here are some profile functions. And, well, there was a couple of interesting things about them. So this was in the global case, and this is the gauge case. None of them look like embedded superconducting vortices. There's a kink in the, I don't know if you can quite see it there, but that red line does not, it's not a straight line through the origin where the vortex is. So basically there's a kink. So it's not represented well by the superconducting vortex profiles. This is an illustration of one of those cases. So this is the red line here is the radial profile that you would get by putting the superconducting vortex in, and this is what we found from the gradient flow. And this is the condensate field, which would be symmetrical in the case of just putting the superconducting vortices in, and it doesn't quite look that way. So basically there's a thin string approximation, the thing that we used in the earlier cases to try and predict what radius you would get. That semi-analytic method does not work here, unfortunately, and that's the bad thing about it. So the kinky Vortons, it all worked very well, but in this case it didn't. So, well, here's some pictures of the solutions. And one last thing before I get cut off. So you can work out the radius as a function of this coupling constant. So as the coupling constant increases, so does the radius. But the interesting thing is that there are some values of Q for which there are solutions where there's no solution at G equals 0, but there are solutions at higher values of G which are smaller in radius. Okay, so let me conclude what I want to say. So we showed these 2D kinky Vorton solutions in U1 cross Z2. We have an analytic solution for the straight string, and we were able to sort of exquisitely understand the stability of these solutions. For 3D Vortons, we found solutions in both the global and the gauge cases, but the thin string approximation doesn't work for these solutions. So we're not able to make quite as much analytic progress as we would have liked. Okay.
Thank you very much.
Are they stable or not in 3D?
Sorry?
Are they stable in 3D or not?
What?
Vortons.
Well, I think it's something that's dynamically stable will always be unstable to something in some regime. But I mean, the kinky Vortons, I think, is there is a.
No, I mean in 3D.
I can't. This is what we did in 2D, and this suggests that there is some regime of chi for which there are things that are stable. Okay, and if unfortunately we can't do the same calculation in 3D, but my presumption is that there is some regime for which they are stable. That's what I believe, but I can't prove or disprove that statement, or even support it with anything other than the things that I've shown.
Yes.
What the two ordered parameters are doing looks different in the solutions, but I can't quite see how the two terms appear differently in the original Lagrangian. That is your phi and sigma. How do they enter it differently?
Yeah, well, they look very similar, as I've written it here, but actually the parameters are, I mean, I haven't gone through the details of the parameters, but the parameters are arranged so that essentially one is in what we call a broken phase, which basically means that there's the lowest energy state is where phi is equal to eta phi, and the other one is not broken. Okay, so they're arranged in such a way as that's.
So eta phi is some finite number, and eta sigma is 0 or negative or something. That can't be.
One is bigger than the other.
One's bigger. That's all. That's really the only difference.
Yeah. Yeah.
Phase
Okay,
separation.
thank you very much, Richard. Let's move on to